Hi everyone. We're at our last keynote for ZuriHac 2020. I hope everyone enjoyed things so far, learned something interesting, and maybe made some new friends as well. Our last speaker is Alexis King. Alexis is the author of Hackett, a language that attempts to combine the best aspects of both Haskell and Racket. She has written a number of extremely good blog posts, for example, Parse Don't Validate. If you haven't read those, I recommend you check them out. So during our talk, if you have any questions, don't forget you can post them in the talk discussion channel on our Discord. And please tag them with either clarification or question so we know if we can ask them during the talk or at the end. The floor is yours, Alexis. Please go ahead.
All right, thank you very much. So I know that where a lot of you are, this is the last talk of ZuriHac. It's the evening, things are winding down. I would love to be able to say that this is going to be a nice, simple, easy talk. Unfortunately, I cannot say that at all. This is an enormously technical talk. So hopefully everybody can stick with me and follow along. But if you have any questions, please feel free to ask them because things will move along relatively quickly. And, if you get lost, it may be a little bit difficult to catch back up. So feel free to interrupt me at any time. So I'm just going to jump right in, and I'm going to start by giving just a little bit of context about what this talk is about, where I'm coming from. I started writing Haskell professionally just about 4 years ago. And at that point in time, what I was working on was basically just a CRUD app. And the really nice thing about working on a CRUD app, although it wasn't maybe the most exciting product in the world, was that performance was not a huge deal. So after I'd been working on that for a couple of years, we started running into a situation where effect management was becoming a problem. And I didn't really have to worry too much about the performance of existing effect systems, even though that's sort of known to be a limitation of effect systems. So at that point in time, in 2017, neither fused effects nor polysemi existed, which are two of the, I think, major contenders in the effect system space, of which there are many today. So I found a library called Freer, which I want to be very clear. The code already existed. It's the work of many other people. I just sort of gave it a fresh coat of paint. But I eventually released it as Freer Simple, even though I didn't even really understand how the internals worked. But that ended up being pretty useful for us. Then at that point in time, just a little bit later, I took a break from writing Haskell to do some researchy stuff for about a year. And then I came back. And about a year ago, I started writing Haskell again. But now I'm working at an entirely different place, doing something entirely different. I'm working at a company called Hasura, which I'm not really going to talk too much about what we do because it's not all that relevant to this talk. But if you go to our website, you'll see that it describes us as providing real-time GraphQL on PostgreSQL. Now, that may not be entirely obvious what that means, but there's sort of a running joke that all functional programming and programming languages people tend to think that every single application in the world is a compiler, and I'm guilty as charged. In this particular case, I think that what we build is really secretly a GraphQL to SQL JIT compiler. Now, if you don't have any idea what GraphQL is, or even if you don't have any idea what SQL is, that's not important because this talk is not about either of those two things. But the reason I want to bring this up is just to focus on these two words, real-time and JIT. We are doing this process, this fairly involved process on the fly in real time, and it's very, very important that it's fast. That is one of the major selling points of our products. So when I started, running into some of the same kinds of problems that I ran into at the first job I worked at, I kind of started to wonder, well, can we actually afford to use an effect system? Is sort of switching from using monotransformers to an effect system, is that a responsible decision, or is it too risky for what we do? So a good place to start to answer that question is to take a look at benchmarks. So let's start by looking at a benchmark. I'm really just going to focus on one benchmark over the course of this talk. There are a lot of different effect system benchmarks that benchmark different things, but I think that this is a particularly good benchmark to illustrate the things that I want to talk about. Here are the benchmark results. I'm going to sort of explain what they mean as we go forward. But I want to start off by saying that lower is better. So right out of the gate, we can see that polysemi is not winning any prizes. Let's take it off this graph because otherwise it just becomes completely impossible to see the other three results. These are the results for the baseline implementation, MTL, and fused effects, and you can see that they're all essentially identical. So if we were to just take these results at face value and answer the question immediately, Can we afford to use an effect system? It seems like the answer is yes, as long as we don't pick polysemi. But of course, it's never actually that simple. Just right out of the gates, there's probably a handful of questions that you might be wondering about when looking at these results. So first of all, what actually is the benchmark? What is the baseline implementation? What does it actually do? Are these differences terribly significant at all? The numbers are in microseconds here. Is that actually going to have a significant impact on anything? And why, oh why, is polysemi so much worse than everything else? So I'm going to answer all these questions, or at least attempt to answer all these questions. But some of them are do not have particularly straightforward answers. Fortunately, the first one does. So let's take a look at the benchmark. The benchmark itself is a micro benchmark, and you can see that it really lives up to its name of being a micro benchmark. It is very small and is composed of just two functions. There's this countdown function and another function named program. So countdown is, this particular benchmark is a benchmark of the state effect. So this countdown function is the entry point to the benchmark. It takes an initial state, it passes it to program, and then program is sort of the bulk of the benchmark. It's a loop. The loop is very, very simple. It just gets the current state, checks if it's less than or equal to 0. If it is less than or equal to 0, then it bails and it returns and the benchmark is done. Otherwise, it decrements the state by 1 and it then loops. So very, very simple. Now, this is the MTL version of the benchmark, but the fused effects and polysemi versions are essentially identical. The reference or the baseline implementation is a little bit simpler, though. It's just something that doesn't use any effect system at all, but does the same thing. It's just an ordinary recursive loop without using any state effect whatsoever. And you can see that in this simplified version, there's actually no difference between the countdown function and the program function. They're just completely identical. All right, so that's what the benchmark is, but probably something that many of you immediately think when you see this benchmark is that this is an incredibly synthetic program, right? Nobody would write this program. Nobody's going to write a loop that reads a piece of state, decrements it, and does absolutely nothing else. So immediately we kind of have to ask ourselves the question, is this a bad benchmark? Is this benchmark telling us anything useful? And I think a lot of the time people are very skeptical, rightly so, of micro benchmarks because it's very easy to overfit to them. It's very easy to end up with a benchmark that doesn't say anything particularly useful. But I'm actually going to defend this particular benchmark. I think that, and I'm going to defend micro benchmarks in general. I think that there are significant advantages to real-world benchmarks, namely that they're a real program, so they kind of have to be representative of something. They're not really going to be a flaw of the benchmarking process because if the performance of a real-world program is good, then you've already won, right? There's no problem. You have made the performance of a real-world program good. That is the goal. But there are problems with using real-world benchmarks. For one, they're really big, so it can be hard to actually understand what they're doing. And it can be difficult to sort of isolate the costs of individual things, which can make it very difficult to use those results, apply those results to other programs, which may be very different. The advantage of micro benchmarks is that you can really isolate costs. You can understand exactly what's happening everywhere in the benchmark. And if you do that, which is a big if, it can be difficult to thoroughly understand what micro benchmarks are doing. But if you can do that, then it's possible to build a mental model of a mental model of how those costs sort of extrapolates to other programs. But they do have significant flaws. So one of the biggest flaws, one of the easiest ways to go wrong is that it's very easy to measure the wrong thing when measuring micro benchmarks. You can end up, because they're so small and because they're so synthetic, it's very easy to end up in a situation where some compiler optimization happens that wouldn't normally happen. And so you actually end up measuring maybe just the cost of the benchmarking harness itself rather than the actual benchmark. It's also very, very important to understand how the results apply because, again, they are so far removed from any real-world program. It's not necessarily clear what they mean, and indeed, they're not considered in context with anything else. So you don't get a nice number like n requests per second. You just get some amount of time. That's not immediately obvious what that number actually means. So maybe you're not entirely convinced by this, but I really think that effect systems are particularly difficult to measure with real-world benchmarks, and having this suite of micro benchmarks is particularly valuable. The reason for that is if you sort of think of some real-world program There might be some part of the program that, say, like parses a query, and maybe you want to benchmark the cost of that. That is something that's going to take an appreciable chunk of time. You can instrument the program, you can, insert some logging, or you can use the profiler to see how much time is spent inside that particular function. And that can give you a pretty good understanding of how much of the runtime is spent right there. But with an effect system, you're going to have some get operations somewhere, some put operations somewhere, some ask operations somewhere, throw operations somewhere. And these are all tiny operations spread out everywhere throughout your program. And that makes it very difficult to actually measure the performance, because any profiling that you do is actually probably going to sort of introduce more overhead than you actually end up spending time in each of these individual functions. So I think that in this particular case, micro-benchmarking is useful and valid, but it may not be immediately clear what this benchmark is actually measuring. So if we look at the benchmark again, and we take a look at what it's doing, sort of the most obvious place where the effect system is involved are these two get and put operations. And so to a first approximation...
Alexis, we have a clarification request from the channel. Someone is asking if strictness is relevant here in this benchmark for the N, or if GEC will be able to figure that out.
That's a good question. I'm simplifying the benchmark a little bit. In this particular case, there is the thunk that's built as a part of the state is forced. It's inserting some additional strictness. But that's a good question. Right, keep going. So let's see, what was that? Yes, so to a first approximation, this benchmark is measuring the cost of the get and put operations, but that's not entirely fair. If we were just measuring the cost of effectful operations, that wouldn't necessarily make a particularly good benchmark. So in order to understand why that might be, you could imagine some hypothetical, really expensive effect operation that does some really expensive things. And if you think about what would happen when you actually call that operation, basically the effect system would look up the handler for that operation. It would then jump to it, execute the code, and then return. And the part that the effect system is responsible for is really just these first and last blocks, right? The amount of time spent looking up the handler and making the call and then returning from the call. The part that's in the middle is not really the effect system's responsibility, because that could just be any arbitrary code. And if it's slow, it'll be slow. So if it were slow, that would be a pretty big problem, because the amount of time spent in these red blocks here on the edges would be essentially irrelevant relative to the amount of time spent in the actual implementation of the function. But that's why the effect that we're using here is the state effect. That's why it's so important to be very careful about the effect that we measure, because this operation, while it tends to be implemented in different ways in different effect systems, is really cheap. So the amount of time that we're spending in the call and the return is actually measurable, and it's appreciable relative to the amount of time actually spent executing the operation. So this allows us to measure specifically the overhead of effect dispatch, the amount of time that the effect system introduces on top of just an ordinary function call. And that's really what this particular benchmark is designed to measure. But it's not the only thing that it's designed to measure. And the other thing that it's designed to measure is the cost of bind. So if we switch from using do notation here to make it a little bit more explicit, we can see that the other sort of two operations the effect system provides that we're running in this loop are both bind, or some derivative of bind. And a lot of the time, I think we tend to think of bind as being free, right? We don't really think too much about the cost of bind, because it's not really something that's doing any of the interesting logic in our program. But nevertheless, the performance of bind is really, really important, because it just shows up everywhere, right? Obviously, it shows up if you use do notation or write bind explicitly, but it also shows up effectively when you're using applicative notation. It shows up in traverse and sequence, and it also shows up in these little monadic combinators. And so in a lot of these uses, we don't even really think about them that much, because they're sort of hidden away, and we're thinking about the logic of our program. But it turns out that the number of bind calls is going to essentially eclipse the number of calls to effectful operations. So it's really, really important that that operation is particularly fast. So to briefly recap, count time is a micro benchmark. It theoretically provides some value, and it measures two things: the cost, the overhead of effect dispatch, and the cost of bind. Now, it might not be immediately clear to you why I'm spending so much time going over every minute detail of this benchmark. Why am I belaboring this? I've spent about 10 minutes now talking about this very, very silly, simple benchmark. And the answer is that the results are totally bogus, or at least very highly misleading. So even though I've spent a bunch of time defending this benchmark and the quality of this benchmark, the results are, in fact, pretty much totally wrong. So in order to understand why that is and what's going wrong, consider that in the original version of this program, we defined both these functions in the same module. If this benchmark is worth anything, we should be able to split the two functions into two separate modules, and the performance should not change. If it does, that's really bad, because most Haskell programs are not one module large. So it's really, really important that this does not affect the benchmark. If it does, it should be really, or it would be very troubling. But indeed, if we start with the benchmark results that we just saw, and we split the two functions into separate modules and then rerun them, we get this, which is not good. If we compare the two results side by side, you can see that there's a pretty enormous change. If we once again zoom in on MTL and fused effects, you can specifically see that the change in fused effects is about 2 orders of magnitude, which is enormous and is very, very bad. And it should start raising all kinds of red flags about the quality of this benchmark. So what is actually happening? Well, if we take a look at the results, there's kind of immediately sort of a smoking gun. If you look at the polysemi change, it's actually very small, right? The results changed a little bit, but not that much. And this is not terribly shocking. This is reasonable. This probably indicates that polysemi isn't really cheating too much at the benchmark. But the changes here are enormous. And that's pretty much a smoking gun for the fact that this is that MTL and fused effects are overly reliant on the GHZ optimizer. So the takeaways from this are that MTL and fused effects are faster than polysemi, even in kind of the multi-module scenario, but they are enormously reliant on compiler optimizations, and tiny changes in the program can create huge differences in performance, which is very worrying. Because of course we might start wondering, is this actually something that we can rely on? When are we actually going to get the good performance? When are we going to get the bad performance? And in order to answer that question, it's important to understand what's actually going on. So I'd like to now take a little bit of time and bite the bullet, go into the details of how these different effect systems are implemented, what's going on under the hood. And there's essentially 2 implementation strategies for effect systems out there in the wild. One is to use monad transformers and type classes. This is kind of the conventional, traditional approach. It's generally believed to be pretty fast. It can be kind of complicated and require a lot of boilerplate. This is the approach taken by MTL and fused effects. And I include both of them because MTL isn't really an effect system per se, but it can be sort of used as an effect system. And fused effects is very similar. It's using essentially the same implementation technique and adding a little bit of extra machinery to type level machinery to make it behave closer to what people come to expect out of an effect system. Most of the other approaches use free monads or free-like monads. Not quite free monads, but same general idea. And these are very nice because they're extraordinarily flexible and they can provide a simpler API, but they're known to have performance limitations. Polysemi and free or simple are both examples of effect libraries that use free monads. And in this particular talk, I've chosen to use polysemi as sort of a representative example. If you look at the results for other effect systems that use the same implementation strategy, the constant factors tend to be a little bit different. Sometimes there can be minor variations in the asymptotics, but they're essentially the same. So if you're curious about what some other effect system performs, it probably performs a little bit, performs similarly to polysemi. So I want to focus on the implementation of the implementation strategy of free monads first, because I think it's actually a little bit simpler to understand what's actually going on. The idea behind free monads is that if we take a program like Countdown and we see all these different operations like get and bind and return and put, we can just sort of provide an interpretation of them that is no interpretation. We can just replace all of them with data constructors. And this is very nice because we're actually building up a value, an ordinary Haskell value, a sort of tree of functions and data types or data constructors that we can then interpret later, and we can provide whatever interpretation we want. So what are actually the definitions of these 2 types, this EFF monad and the state type that we pass to it, they're actually extraordinarily simple. The EFF type, this EFF monad, is just an ordinary GADT with 2 data constructors. The state type is also just an ordinary GADT with 2 data constructors. And then we can write an interpreter that just is an ordinary Haskell function. It does ordinary pattern matching on these ordinary data types. For recursive, we walk the program, and each time we see an effectful operation, we provide some kind of interpretation to it, and eventually we reach return, and we're done. And while real implementations, real effect systems tend to be a little bit more complicated than this to either improve the performance or to provide some slightly more advanced functionality, this is really the core idea. And it's very, very nice because it's just sort of almost beautifully elegant, and it's extremely flexible because, again, it's just like you interpret this data structure just with an ordinary Haskell function. And that means that you have your full complement of term-level programming tools available to you to decide what the program means and what behavior you want to give to each operation. But it's sort of immediately clear, I think, where some of the performance overhead is coming from. For one, we actually have to reify the entire program as a tree. And that takes time. It takes time to construct the tree. It takes time to interpret the tree. And the tree has to live in memory, which means it's taking up memory. But this is actually, I think, not even the most significant cost. I think the real significant overhead of this approach is that it obscures the structure of the program to the optimizer. GHC sees this program, and it doesn't really know what to do with it. It just sees a bunch of data constructors that are applied to things, and it says, all right, great, that's fine. I'm not really going to touch this. Now, it might not be immediately clear how it could do better. But in order to illustrate how it can do better, I want to sort of like walk through the way that the optimizer sees the program when using ordinary monad transformers, not using MTL, not using monad state, just the ordinary state monad. So we use the ordinary state monad with totally bog standard ordinary implementations of return and bind, totally ordinary implementations of get inputs. We can take this monad and we can use this to implement our exact same program. So what changes relative to the free monad approach? Well, immediately, GHC is going to start looking at these operations, and it's going to say, okay, I can inline these, right? Because now these are function calls. They're not just data constructors. Now, if we start inlining them, we immediately get kind of this incomprehensible mess. But it turns out that a lot of this mess is just wrapping and unwrapping the state new type. It turns out from the optimizer's perspective, new types are sort of irrelevant. They're not really all that much different from type aliases. So we can, in this particular case, just kind of ignore that. And now to the optimizer, this just looks like an ordinary function that takes an int and returns a pair of ints. And now the optimizer can keep going, and it can, continue to inline things. So we can inline return. It turns out return in the state monad just takes the 2 arguments and wraps them into a tuple. Inline put, which just throws the second argument away, which is the state, and then returns the new state. And this is where things get interesting. So far, this inlining, while maybe it saved us the cost of a function call here and there, it hasn't really been all that important. But now you can see that we're constructing a tuple, and then we're immediately pattern matching on it. And this is where the real performance advantages come, because now GHC can just eliminate that case expression. It can effectively evaluate that case expression at compile time. And so at this point, we've now eliminated an entire sort of thing that the program did just by inlining and simplifying. We can do the same thing for get. We inline get, now we're constructing a tuple and pattern matching on it immediately. We can evaluate that at compile time, and lo and behold, we have a very nice, simple program. And in fact, not only do we have a very nice, simple program, but if you compare this to the baseline implementation that we saw earlier, it is exactly the same, save variable name. So it's exactly the same program. And this is indicative of why monad transformers are so effective. To sort of borrow a term from the Rust community, they're effectively zero-cost abstractions. The optimizer is able to eliminate the overhead by doing nothing except inlining the actual operations and then sort of cleaning up the program. And it doesn't really have to do anything more than that. So the optimizations are pretty predictable, and they're not particularly reliant on quirks of the compiler optimization process. So, okay, this is all well and good, but this is not actually an effect system, right? Here we've now coupled ourselves to a particular state monad, a particular state implementation. We can't swap it out. And in fact, we can't even use this in some other monad transformer stack that has state somewhere inside of it, but not at the base, right? So what we really want is we want to get the performance of monad transformers. We want to still have the flexibility of free monads. And I think that's kind of a good way to think about this is that it's actually very similar to the list fusion problem. It might not be immediately obvious why I say that, but if you sort of look at what list fusion is, the idea is that in some expressions that operate on list, you have list producers and list consumers. And if you were to just kind of evaluate this naively, then you would build up a list and you would feed the elements one by one to full DAR. Now, it would be lazy because Haskell is a lazy programming language, but eventually you still have to pay the cost of allocating each one of those constants and feeding the elements one by one to full DAR, which then recursively loops over them. And this is kind of silly because if you look at sort of the list itself, what you could do is just sort of statically at compile time, replace the cons operation with plus, or replace nil with 0, and you would get an expression that does exactly the same thing, but the list has now completely disappeared from the program. And now we're just directly, directly adding these numbers together in a little recursive loop. And this is something that is sort of implemented in GHC using read-write rules, but it's kind of finicky. And it doesn't always fire, but it does work sometimes, and it gets significant performance benefits when it does. If you look at the free monad approach, it's actually very similar, right? We have some code that builds up a data structure, and this is a producer. We have some code that interprets that data structure with a recursive function. This is a consumer. And ideally, we would like to be able to kind of replace all of these operations with the fast versions of those operations that we defined with the state monad transformer. So the question is there some way that we can get GHC, that we can convince GHC to do that for us? And our hope is that MTL can do better than free in this regard. Our hope is that MTL somehow, and sort of the conventional wisdom, is that MTL somehow enables the compiler to make this optimization, even though with free monads it cannot. And based on the benchmark results that we saw, there is some reason to suspect that that's the case, but it might not be immediately obvious why. Because in order to answer this question, we have to understand what this program is doing. We have to understand how this program is compiled. But it's not as easy to understand as with the other approaches because we've got these operations that are now coming from this type class constraint. But I think a lot of the time Haskell programmers don't have a great operational understanding of how type classes are compiled because it's actually, it's kind of complicated. It's not the most straightforward thing in the world. It's a little bit subtle how type classes are compiled. So I want to explain how type classes are compiled so that I can sort of provide some intuition for what's actually going on here. But I want to start with two examples of how type classes, sort of solutions that don't work for compiling type classes to explain why the solution that GHC takes is the solution GHC takes. So the simplest, most naive solution that does not work is type dispatch. So this is, I think, kind of the way that a lot of people think of type classes. If you have some operation like show, you could think of it as being implemented by looking at the type of its argument and then doing dispatch on it using some hypothetical syntax. This is not real Haskell. There is no type of operation. And that's actually sort of fundamental. That's sort of the problem with this. I mean, there's sort of two problems with this. One is that it would require a whole program compilation, right? We would need to know all the different types that show operates on when we compile show, which is not viable because, of course, show is defined in base, and you can define show type class instances on your own data types. But the deeper problem is that GHC performs full type erasure. So the information, looking up the type of a value is just not possible. To make that more concrete, in Java, you can. For example, you can check whether an object belongs to a particular class at runtime. And the reason for that, excuse me. The reason for that is that the representation of an object in memory in Java includes a pointer to some object in memory that represents its class. And you can actually look up that value, and you can compare it at runtime. But Haskell data types, if you have a value of a Haskell data type, it doesn't have any tag associated with it that says, I am a foo. It's just the data that's stored in the data type. It's just some bits floating around in memory. And this is a little bit of a simplification. It's a little bit more complicated than this in practice, but it is effectively true that in general, you cannot necessarily distinguish what type a value is that's sitting in memory. And this is very nice because it means we don't have to track all this stuff, but it does mean that we fundamentally can't have an arbitrary type dispatch operation. So a different approach we might come up with is kind of the complete opposite. The first approach was to kind of do this reflectively at runtime. The second one is to do all of this at compile time through something called monomorphization, which is a very scary sounding term, but it's actually very simple. Here's the idea. Suppose we have some function that is an overloaded function. It's defined on, it has some type plus constraint. And in this particular example, it's a very, very simple function called exclaim that just calls show on a value and then appends a bang to it. So the idea behind monomorphization is that when we go to compile this function, we actually do nothing. We do not generate any code for it whatsoever, but what we do is we store the definition of this function in the interface file. Now, what is the interface file? Some people watching this may not be aware, but every time GC compiles a Haskell source file, it actually generates two built products. It generates a .o file, which is the compiled native code, but also generates a .hi file, which is a Haskell interface. The .hi file is sort of the replacement for if you've written C or C++ header files. It's sort of like having automatically generated header files. It includes all the type definitions, type declarations. It includes the types of all exported bindings. But it also does a little bit more than what header files do. It also includes the source code of small bindings. And this is used by the inliner so that it can do cross-module inlining. So if you define a function in one module, somehow GHC needs to know what its definition is to inline it in another module, so it will store it in the interface file. But it doesn't store all definitions in the interface file because that would make compilation slower, because every time you compile a module, you would have to actually spend time loading all those definitions. With monomorphization, we would have to store the source code of all overloaded bindings in the interface file, which would cause compile time to get a little bit slower, but that's not actually the worst of it. So why do we have to do that? Well, because the way monomorphization works is every time we actually see a call to an overloaded function, we essentially on the fly look up its definition and then generate a monomorphized or specialized version of that function based on the type that's called at. So in this particular case, we're applying it to a bool. So we would generate an exclaim bool function that operates on bools. Now, the really nice thing about this is that, I also forgot. Then we rewrite the original call site to call exclaim bool. The really nice thing about this, though, is that overloading is totally free. It has essentially zero runtime cost, because what we're doing is generating at compile time the same code that we would have generated if we had just written the original function specialized to Booleans, right? GHC is essentially doing that specialization for us. However, there is a significant downside to this, namely that it can create a lot of code bloat. So if we have, for example, 3 different calls to exclaim at 3 different types, then we generate 3 copies of the function. And for exclaim, this isn't really a big deal because exclaim is really tiny. And generating 3 copies of exclaim is probably not really actually that much of a problem. But Haskell programmers are generally totally happy to write giant functions that are overloaded. And in fact, we can imagine we might even have some function that is overloaded at 3 different types. And this means that any combination of those 3 types will generate a separate copy of that function. Now, okay, what are some of the problems with this? Well, it bloats the executable size, which is obviously bad. Smaller executables are nice. It can actually have an impact on runtime cost, since code bloat can cause less of the program to fit into the cache at once, which can cause more cache misses, which can in turn slow your program down. But also it just makes compile times enormously larger, because GHC actually has to compile every single variation, every single specialized variation of these functions. So C++ and Rust programmers are very familiar with this. They are sort of, so yes, it's good for runtime performance, can grab the code size. C++ and Rust programmers have to worry about this. They do worry about this. They tend to think about how big the function is that they are sort of defining when they're either defining a template or a trait. But Haskell programmers generally don't, right? In the same way that Haskell programmers don't think that much about manual memory management, they also don't really think that much about how much code is going to be generated by specialized copies of their functions. And I think that's, for the most part, a good thing. I think it would be unfortunate to have to worry about this all the time, but it does mean that we need a different implementation strategy. So let's talk about how type classes are actually compiled. So it's actually kind of a clever trick. Here's the idea. We start with the original function, and instead of compiling it directly, we essentially do a compile time transformation of this function into a higher order function. So instead of having the show a constraint on the function, we pass in a function from a to string, which is sort of the version of show that we're going to call this function with. And then when we actually see the call side, see a call to this function, if, for example, we're calling it on a Boolean, we just pass as an additional argument. The compiler inserts an additional argument to this function that passes show on Booleans. And this is really great, right? Because now it doesn't matter how many different implementations we have, we just generate a slightly different call site with a slightly different function. And so we can compile the original function exactly once, and then we can use it at all the code sites, and there's no code duplication. So of course, this is a slight simplification, because in reality, show actually has 3 different methods, not just one. And so in that particular case, GHC, it could pass them all around as separate arguments, but GHC decides to pack them up into a record. So, excuse me. Yes, it decides to pack them all up into a record. So it turns out that at compile time, GHC essentially implicitly translates every type class definition into a record definition, and every type class method definition into a record selector definition. And these records are called dictionaries, which is why this approach tends to be called dictionary passing. And then what we can do is we can just pass the entire dictionary around, and all we have to do when we actually want to call the show function is pull the show function out of the dictionary and then apply it to an argument. So this is dictionary passing. It's extremely simple. It's actually very, very nice. It's almost, it almost seems sort of too simple to work out. And it's very cheap to compile, because we only have to compile each overloaded function once, and the additional work of inserting those additional arguments is not terribly significant. But does raise the question of whether or not this has a runtime cost. So to answer that question, let's take a look at the MTL version of this benchmark. If we were to translate this into dictionary passing, what we would have to do is bring in a dictionary for monad state. And in this case, the monad state dictionary also contains a dictionary for the monad class, because monad is a superclass of monad state. So the dictionary is packed up inside of it. And now we have to make all of these sort of infix calls, prefix calls, because we have to pass the monad dictionary to bind into the sequencing operation, which makes the program look pretty awkward. But otherwise, it's essentially the same. We're calling bind here, and we're also passing the state dictionary to get input. So now we can actually talk a little bit about how GHC compiles this function, and we can wonder, is this going to be as performant as the transformers approach? And the answer is no, unfortunately, because now, once again, we can't inline anything. Just like we couldn't inline data constructors because, well, they're data constructors. We can't inline these things because they come from the function definition, right? They're actually passed in as arguments. They are lambda bound, so to speak. So this is the difference between what in GHC are known as, or I guess compilers in general, are known as known versus unknown calls. Most calls are known calls. So if you have, like, for example, a particular function, you apply it to some arguments, most of the time the compiler can look up that function. It can figure out where it's defined, various pieces of information about it, including its definition, the strictness it has, lots of metadata that the optimizer stores alongside each function. And this means that if the compiler wants, it can inline the definition, and then it can later simplify it. And that's all very, very nice. But higher order functions involve making unknown calls to unknown functions. So for example, if we have something like fold_r, then this f function is passed in as an argument to the function. So if GHC looks up, what its definition is, it has no idea, because the caller of fold_r decides what the definition is. This is a really big problem, because unknown calls are effectively hard barriers for the optimizer. There's all kinds of information that known calls provide that unknown calls simply can't, because GHC doesn't know what the function is. Known calls, one very minor difference is that known calls are compiled to direct jumps, while unknown calls are compiled to indirect jumps. This doesn't really matter. The direct jumps are maybe slightly faster, but not a big deal overall. The real differences arise from the fact that known calls expose strictness information, which in turn exposes more optimizations. Unknown calls have to be pessimistically assumed to be lazy in all arguments. Known calls arguments can be unboxed. Unknown calls cannot, because they have to use the declare type as the calling convention, because GHC can't do anything special for those functions because it doesn't know what they are. Known calls can be rewritten by rewrite rules. Unknown calls fundamentally have to be opaque. And as I mentioned, known calls can be inlined if they're sufficiently small, while unknown calls are never inlined. So this is one of the major costs of GHC being an ahead-of-time compiler, right? A lot of other major high-level programming languages are implemented with a JIT compiler, which means that they can actually take advantage of runtime information. If there's some kind of dynamic dispatch going on, they can learn about that at runtime and then optimize the program based on that. But GHC cannot. So if it doesn't know something statically, it can't ever optimize for it. And GHC doesn't really do any sort of profile-guided optimization either. So we're kind of stuck with what we have. So type class overloading creates a bunch of these unknown calls because we're passing around these dictionaries and then pulling functions out of those records, which is just the same as passing the functions to, or passing functions to functions directly. And that means that overloading is not free. It means that overloading has a performance cost. And I think that sometimes that can be a little bit surprising because we don't, again, think too much about the cost of type classes. We don't think too much about the operational semantics of type classes. But I think it's important to keep in mind that this is not as bad as it might seem. I'm kind of playing up the disadvantages here. Normally, they're not that bad. Unknown calls are not a death sentence. For example, suppose we have some function. This is a kind of weird example function that would never exist outside of a presentation, but it's a function that computes all the indices that a particular value appears at in a list, and then it sums them. I don't know why you'd ever want to do that, but that's what this function does. And somewhere in this function, we have an unknown call to this equals function. And even though this is an unknown call, it really doesn't have any impact on the overall performance of this function because it doesn't prevent list fusion from happening, right? That's what's really going to be important in the definition of this function, is that we want the zip, filter, map, sum. We want all those calls to fuse together. And there's nothing about the fact that equals is an unknown call that prevents that from happening, because for the most part, basically it doesn't exist in between any of these functions. So it can just be treated as a black box and the fusion can still happen. The reason that bind is such a problem, unknown calls to bind are such a big deal, is because bind lives in between all these different operations. So if we look at, for example, something like this, where we have some part of this monadic code that returns some list, and then later in the monadic code, it sums that list, even though there's bind in between that list and where it's summed, because GHC can inline bind in this particular program, because we're programming against a concrete monad either, GHC will actually still perform list fusion on this. The fact that there's bind in between is not a problem. But if we were to generalize this from operating on either to operating on monad error, we can no longer perform list fusion on this program because we're performing an unknown call to bind. This is now totally opaque, and GHC doesn't have any idea what it is, so it does not know that it can sort of fuse the sum and the list construction together. Bind is glue between different parts of the program. And for that reason, it's especially crucial that GHC can see through it, because it exposes optimizations from adjacent parts of the program. And that's why this the overhead of MTL is so significant. It's not particularly surprising that MTL has a cost viewed through this lens, but it does make us sometimes wonder why it's sometimes fast and sometimes slow. So the reason for that is there is another piece to this puzzle, which is specialization. So the good news is that I don't have to spend too much time talking about specialization, because I actually kind of already explained it. Specialization is monomorphization. It's just monomorphization in limited circumstances. It's monomorphization as an optimization rather than as a compilation strategy. So the idea behind the specialization pass in the optimizer is that GHC searches the program for any calls to overloaded functions at known types, and that function must satisfy at least one of the following criteria to be specialized. One, it can be defined in the current module. Two, it could be declared with an inlineable pragma, Or 3, it could be a class method and its unfolding, which is the bit of source code that's stored in the interface file for the inliner, is actually stored in the interface file. Why is that second condition true? Because it sort of, GHC needs to have the source code of a function to specialize it because it has to generate a copy of the function. Not terribly shocking. So these second two cases are sort of interesting abstractly, but they really don't apply to what we've been talking about because we've never even once seen an inlineable pragma in this talk. And that third one only applies to class methods, which is really just kind of an ad hoc heuristic. In this particular case, we're not defining any class methods. But this one is clearly relevant to the situation that we're running into, right? Because it involves whether or not something's in the current module. And indeed, that is the answer to this puzzle. What happens when the program is when the program is called from the same module that it's defined in, the specialization pass kicks in. GHC translates this to the version of the code that operates against a concrete state monad, and all of those nice optimizations that I talked about earlier immediately kick in, and we get the nice fast code. When it's defined in a separate module, then the specializer doesn't kick in, and so it's compiled in the usual way. It's compiled the dictionary passing. That has a bunch of unknown calls. Inlining doesn't happen. Things are slow. So it's a lot of context to explain this, but finally, we've gotten to the answer. Now, it might seem like this was kind of a roundabout way of explaining this. I really could have just told you, well, the answer is that the specializer only works for calls that are defined in the same module. Why did I bother going through this entire process? Well, because I'm not quite done. The goal here is not just to understand what's going wrong. The real goal here is to understand if we can fix it. So, can we avoid this performance regression? Well, unfortunately, not really. The function has to be, has to satisfy one of these 3 criteria. It's not going to be the last one. Maybe it could be the second one. We could add an inlineable pragma to this function. But we can't really add an inlineable pragma to all of our functions in real programs for a few different reasons. One, it would just be frankly annoying. But the real problem with it is that it essentially requires GHC to do whole program specialization. So what this means is that at some point in your program, you're going to have some main function that sort of discharges all the effects. And at that point in time, GHC is going to try to compile a copy of every function in your program, which is going to take a lot of memory, and it's probably not even going to finish if your program is sufficiently large. I've tried this on a few real-world code bases, and it doesn't really work terribly well. So this cost is also then going to be incurred not just once, but once for every single specialization of these functions. So if you have tests that run things against a different set of implementations, then you have to recompile all of your programs once per test, which is, again, just really not going to fly. So this also can sometimes be defeated. Sometimes the specialization pass, there's actually a few different things that can defeat specialization. Sometimes, it just doesn't work, but that's normally compiler bugs. But for example, existential quantification is one example of if you pack a dictionary into a data type, then GHC doesn't know what the type is going to be at compile time, and it has to use dictionary passing anyway. So there's various reasons that I think whole program specialization is really not viable. And I think that pursuing this is a lost cause, and it's hopeless, and we really probably should not commit to trying to get whole program specialization. So let's take a step back. Do we really need specialization? Is this really necessary in this particular program? And I'm going to argue that no, we don't. So I'm going to make 2 propositions. One, effect systems are about dynamic dispatch. This is the whole idea. Well, okay, not the whole idea, but one of the main ideas of effect systems is dynamic dispatch. So if you look at a particular program written using an effect system, the purpose of the effect system is to dynamically provide an interpretation of these 2 operations that may be far away from where the function is originally defined. That is kind of the major idea between having effects and effect handlers. This interpretation can be decided later. The second idea is that effect dispatch really is not fundamentally flawed. I think that dynamic dispatch, it is a little bit more expensive, but as I sort of talked about earlier, unknown calls are not fundamentally a problem, right? The real problem here is bind. So how can we avoid that? Well, passing bind via dictionary passing creates problems because it gets called a lot, it's glue, and it's actually one third and final point that I'm now almost wondering, since it's been about 50 minutes if I should talk about, but I'm going to talk about it very briefly. So bind is also using bind also increases, or having bind being an unknown call also increases closure allocation. And it's kind of subtle why this happens. But essentially, when bind is a known call and it gets inlined, then I arbitrarily decided to choose either here. It doesn't really matter. You'll end up with something like this. So what is different about these two functions? Well, if we're using dictionary passing, then when we pass in this y argument, which is an argument to this function, in the first case, y is used under a lambda. And in the second case, it's used in the right-hand side of a case expression. It might not be clear why these two things are different, but they actually are. In the first case, it means that y has to be captured by that closure that gets allocated. In the second case, it means that y can be stored on the stack. And this is kind of seems like a minor difference, but it actually can make a significant difference. It means that when you have code that's, passing all these lambdas around, it means that you're going to be allocating tons and tons of additional closures. I think this is something that people often don't really anticipate because we don't really think about the cost of closure allocation. But I think it's particularly interesting because it means that a bind is an unknown call. The caller must allocate a closure for the continuation. And that means that when we're doing dictionary passing for bind, the entire program is still reified as a tree. It's just a tree of lambdas rather than data types. And this, to me, was particularly fascinating when I discovered this, because it means that if you look at these two programs, one using the free approach that's using data constructors, and one that's using the MTL approach of dictionary passing, in this case, we're allocating a bunch of data constructors, but in this case, we're allocating a bunch of closures. Not quite as many because we're only doing it once per bind rather than once per sort of effectual operation. But these aren't even that different. And that's kind of, I don't know, totally counterintuitive to me, that these two totally different implementation strategies can end up having very similar performance characteristics. So in both cases, you essentially end up walking a tree of closures, which is obviously not great. So how do we escape this hellhole that we've ended up in? Because it seems like even though we've tried two totally different approaches, we've ended up exactly in the same place. And that's pretty discouraging. So here is my proposed escape plan from the world of effect systems. One, we need to have a monad with an inlineable bind for all the reasons that I talked about, and it's important that bind does not allocate, just because it shows up so often, and having bind allocate is not really necessary. It's really just doing one thing and then doing another thing. So we also want to be able, we kind of have to be able to handle all algebraic effects. Satisfying these properties is not too hard if you're willing to sort of compromise on maybe we don't care about coroutines, maybe we don't care about non-determinism. But I think that sometimes those things are useful. And if we want to, using an effect system is such a huge commitment. You're sort of trusting it to underpin everything in your application. I think it's important that it can handle everything that you would possibly need it to. But I'm willing to make a concession, which is that I'm willing to allow effect dispatch to be dynamic as long as the dispatch itself is fast. However, even with that concession, this is not a small order. Requirements 2 and 3 are especially challenging. And the reason that they're especially challenging, I'll get to that. So monad transformers are totally out of the question because fundamentally the effect behavior has to be a part of the bind operation. And that means that we can't make bind inlineable, right? Because bind would then depend on the interpretation of the effects and we can't inline it. But free-to-like monads are also immediately disqualified because bind must allocate to build that tree, which means that it violates the bind does not allocate rule. So what do we do? What do we have left? We've sort of tried every option. Well, there's one that I think we haven't quite tried. It's not particularly well known to the Haskell community, I think because delimited continuations are very closely connected to monads. Haskell programmers have traditionally been attracted to monads, but delimited continuations are known to be deeply connected to algebraic effects. And in fact, in other implementations, virtually every other implementation of algebraic effects, they're implemented using delimited continuations, not monad transformers or monads. Now, I think it's important to note that this is well outside the scope of this talk. This talk has covered just about everything under the sun, and I think if I tried to add another thing to it, everybody's brains would explode. So I'm not going to talk about delimited continuations because they are known to be confusing. But I'm just going to kind of gloss over them. The idea is that we can basically provide two super, super powerful control operations that we can then use to implement everything, and bind doesn't need to know about anything specific to the individual effect behavior, which sounds great. But the problem that I then ran into immediately after trying to implement this is that the only way to implement delimited continuations in Haskell is via continuation passing style. And, well, again, I really don't want to kind of get into continuation passing style because that would involve talking about continuations. I don't want to do that. Basically, if you kind of squint your eyes, the important thing to notice is that in sort of the continuation monad, there's a lambda in there, and that lambda is going to, still allocate a closure. Bind is still going to allocate. Any call to a non-inlined monadic function is still going to have to pass a closure around, and it's going to obscure certain optimizations, and we haven't really done any better than free monads, which is sort of disappointing. So if you actually sort of try this, I tried this at one point and I benchmarked it. This was about, I don't know, 5 or 6 months ago now. It seems to do decently enough for continuation happy code that calls a lot of continuations, but effects that don't need them, like state and reader and error, which are very, very common, have to still pay this cost. And I wasn't really happy with that because I feel like that's sort of unreasonable. I think you should, for the most part, only pay for what you use. So at this point, I decided to just sort of look for some solution, any solution I could find. And I found that there are, in fact, well-known efficient implementation techniques for delimited continuations. But we can't use them in Haskell. There's no way to actually implement them in Haskell. They would have to be at a lower level. So at this point, I just decided that I was going to give up and patch GHC. So some of you may be aware that I have an open GHC proposal to add sort of very, very low level, very unsafe primitive operations for delimited continuations to the GHC runtime. And then I implemented an effect system in terms of that. Now, again, I'm not going to spend too much time talking about this effect system because, again, talked about just too many things over the course of this talk, but I do want to sort of give an overview. First of all, it is open source. You can take a look at it if you want, though it does, again, depend on a fork of GHC, so it's probably not super useful to most people. But I want to talk about some of the key features just as a super high-level overview. The API is very similar to other free-like approaches. So if you sort of like the API of polysemi, then the EFF API is very, very similar. It just provides a single monad, which is crucial because if we're writing against a polymorphic monad, then we can't inline bind. It has to be a concrete monad if we want to be able to inline bind. So we have a concrete monad. But the implementation is totally different from free monads. It's essentially just implemented as reader T over state T or IO. It's actually at a low enough level that the difference between ST and IO kind of disappears. And the reader context holds the current set of handlers, and then it sort of wraps these very, very, very unsafe primitive operations for delimited continuations in a safe API. The effect dispatch is very carefully arranged so that effect dispatch is constant time, and it is faster for most cases than on specialized MTL. Now, that's a bold claim, but of course, I'm sure everybody wants to see the numbers, so fine, let's see the numbers. Here are the numbers, it's great. The numbers are generally pretty good. And something that I want to particularly point out is that there is zero difference between the single module and multi-module case. And this might not seem like a super meaningful thing to point out, but it actually really is, because this means that the performance of EFF does not perform or does not depend on compiler optimizations in any way. And this is something that I think is more significant than people give it credit for, because if the performance of EFF is sort of fundamentally, inherently fast, there's no way to, misuse the library and get poor performance. The way that it's implemented is just fundamentally fast. Now, admittedly, some people might be eyeing the difference between the baseline and the EFF numbers, which are still pretty big, right? This is still an order of magnitude difference. Should we be concerned about that? And I, of course, am biased. I'm going to argue no, but I'm going to try and justify that argument. So if we actually look at the countdown benchmark, I'd never actually mentioned why the baseline benchmark is so much faster than everything else. And it turns out that the reason is that it's operating on ints. Ints can be unboxed by the compiler. So GHC will basically generate a copy of this program that is operating on unboxed integers instead of boxed integers. And at that point, it then, when it compiles it to assembly, it takes 8 assembly instructions, which is very, very small. And it's very hard to beat that. That's pretty much as good as you're going to get for a program like this, short of just optimizing the loop out entirely. But I think that it's important to keep in mind that this is extremely, rare. It's very unlikely that in a real world program you're going to have something this extreme. And indeed, if we take the program and we change it from ints to operating on integers, and we make the same change in the EFF benchmark, then the results are not nearly so lopsided. There's still a difference, right? Because we're still paying for that cost of effect dispatch, but it's well within an order of magnitude, within a factor of 3. So that's much better. It's really not quite so bad at all. And again, this is still a pretty contrived example where the actual operations that we're benchmarking are doing essentially nothing. I think in general, the difference between sort of the version without the effect system and the version with the effect system is probably likely to be pretty much irrelevant. So that's about it. This was quite the talk to put together. Originally, I was sort of hoping to talk maybe more about EFF, but it turned out that there's just a lot of context to talk about. So many things that I'm kind of going to go back over them really quickly, because I imagine some people probably got lost somewhere in there. Hopefully not too lost. Hopefully you managed to find your footing. But the takeaways are countdown is a benchmark. The benchmarks bind and effect dispatch. MTL-infused effects rely a lot on compiler optimizations, and particularly optimizations that often aren't really possible, which is sort of unreasonable. EFF closes the gap by being fundamentally fast. Specifically, it exposes more local transformations by having inlineable binds. Limit continuations avoid the need to CPS the program, and for that reason, it does pretty well on benchmarks. So one final point I want to make is that if there is any thesis from this talk that is not specifically about effects, the particular details, it's that numbers are not sufficient if you're reading benchmark results. It's really, really important to understand why we're getting the results that we are, what they mean, and whether or not they're actually representative of something. So finally, just a few closing thoughts before I finish this out. I feel like the end of this talk is a little bit anticlimactic because the story for around EFF is not over yet, right? We still need to add support for a few other things, and of course the proposal still needs to be accepted. And frankly, I still probably at some point need to give a talk about the design of EFF and what's going on under the hood and delimited continuations. Since in this talk I pretty much just glossed over that. But also MTL's performance is, I think, significantly overhyped. This was sort of surprising to me while I was working on this over the past 9 months or so, is that there's sort of a conventional wisdom that MTL is really fast, and it is if you're operating against a concrete transformer stack, but if you're not, it's not that great. And we can do better than that. So I guess in some sense that's maybe not such a bad thing, because I feel like a lot of people are going to say, well, the performance of this doesn't matter, everything's going to be IO bound anyway. But I don't think that's true. I think that's, someone's going to depend on this performance. And if we want the community as a whole to start moving towards using effect systems rather than monad transformers, to actually see broad adoption, I think that it's really important to get the perf story fixed. And so I'm very hopeful that this will move the needle in that direction. And another thing that we need is good real world benchmarks. Even though I do think that micro benchmarks are very nice and very important, I think that it would be great to have real world benchmarks. It's a lot of work to put those together, but if somebody wanted to volunteer some of their time or organize some effort, I think that would be enormously helpful. And finally, I think that's maybe someday, I haven't thought about this too much, but maybe someday we can close the gap the rest of the way by adding some sort of effect specialization pass, maybe add a GHC plugin or something like that. So things to think about. That's it. I'm done. I will take any questions if you have them. Thank you very much. It's been a pleasure.
Thank you, Alexis. That was wonderful. A lot of people were very happy about the talk and are even wondering if you will do a follow-up talk with all the gory details. And Taylor even suggested that we turn it into a Netflix series.
We'll see how that flies to the executives.
There's a few questions. So someone is wondering in which kind of contexts these performance optimizations are necessary.
in what kind of context these
So,
performance optimizations are necessary?
does it, which kind of applications and libraries require these kind of optimizations?
Oh, I see. Yeah, that's a very good question. When are these optimizations actually going to matter? I think that's a great question, and it's actually a question that I don't think currently I have a super great answer to, unfortunately, because again, we don't have a ton of real world benchmarks for effect systems. But I think generally the rule of thumb is that the overhead of effect systems are probably going to matter if you have code that is using a lot of effects and is actually compute bound, not IO bound, which admittedly is not super common. So if you're doing something that's IO bound, then maybe it doesn't matter as much. But I think that it's still useful to as I sort of said earlier, I think it's still useful to try and get this to a point where it's as good as possible, because effect systems are just so foundational that it's hard to predict how people will use them and what use cases they'll have. So I think that basically my philosophy is just get it to a place where it's irrelevant, that nobody has to worry about it.
Another question that we have is how did you learn all this? Do you have any good resources to read up on the GC optimizer?
That's also a very good question. I think that the best resource that is sort of the least appreciated resource in the Haskell community is the GHC User's Guide. The GHC User's Guide is amazing. It's very nicely written. It contains a lot of information, and it's not always sort of the easiest to find all that information, but there is a lot of really good stuff in there. And if you read sort of the sections on inline pragmas, specialized pragmas, it contains some information in there. Unfortunately, I think there's actually not beyond that a ton of great resources. A lot of this was stuff that I learned through great, painful month-long labor of staring at the dumped GHC core and experimenting with different things and going down a lot of false paths that turned out to not work out. So I mean, this has been the distillation of, as I sort of alluded to, the past 9 months of work, which is why there's so many things to talk about. But yeah, I don't have any great answers to that question, but hopefully this will add just a little bit more to the pool of resources.
Thank you. A few more questions. So could we get a very simple explanation, maybe like an elevator pitch, about what prompt and control do in the proposal?
Yes. So the idea of delimited continuations is that you can essentially capture and restore parts of the call stack. So to give a good way to think about it is that it's sort of first-class support for implementing coroutines, where at some point you can sort of say, okay, I'm going to sort of install an effect handler, and then at some point while executing the program, I'm going to say, all right, I want to yield to the handler. And so what happens is basically the code will stop executing and it'll jump back to the handler, but then it passes it a continuation object, a continuation reference that later on you can then call, which will jump back into the spot that you suspended from. And the fast implementation is basically the idea is that you can implement that as literally just copying slices of the runtime call stack around. And that's what the primitive operations do. And it turns out that it wasn't actually that difficult to implement, because surprisingly, there was actually, GHC kind of already does that in some situations around async exceptions and thunks. So if you want all the gory details, you can look at the proposal, but that's the high level idea.
Follow-up question. Do you think this proposal could have other sort of benefits except for making F possible?
I do. And the proposal, if you read it, there's a little bit of discussion of that, especially if you look at the end, which talks about kind of the design space of continuations. Continuations are extremely flexible. Delimited continuations are known to be sort of equivalent in expressive power to monads. So, you can do a lot of things with monads. You can do a lot of things with delimited continuations. That said, I feel like algebraic effects are kind of, I forget who, I'm blanking on who said this, but somebody once sort of described algebraic effects as sort of like the structured programming, the while and if to delimited continuations, relative to what while and if were to Goto. And I think that's an apt description. So I think for that reason, using algebraic effects is sort of the general thing that you can do with delimited continuations. They're just a nice API to delimited continuations.
Right. Maybe one or two more questions. does the amount of effects that you have in sort of a given stack, does it affect the performance?
That's also a very good question. There is, if you look at this link here on this last slide, there is another benchmark that actually tests that, which tests the performance of, basically different stacks of different effect stacks of different depth. And for EFF, the answer is, well, okay, I should say for a few different things. For MTL, the answer is sort of, because the answer for MTL is it depends. MTL is very complicated. For sort of the free-based approaches, the answer is yes. It tends to increase, like the cost of bind tends to increase linearly in the number of effects that you have, but not exponentially or anything like that. In the case of EFF, effect dispatch is always constant time, and it doesn't change at all based on the number of effects that you have, but the cost of installing a handler gets very, very slightly slower. And if you capture a larger continuation, then that takes a little bit more time. So all the details are still a little bit complicated. But that said, the differences are very small. And given that nobody's going to have thousands or millions of effects, right? Maybe they'll at most have a few hundred. It's essentially constant time. The difference is not significant.
Okay, that's great. Maybe two more questions. So we've mostly talked about performance so far. Can you compare F against the other options out there in terms of features as well?
Yes. So the idea behind EFF is to have kind of a API that is both, in my opinion, simpler than every single other effect system API out there, and as expressive and more performant. I kind of want to have my cake and eat it too, so to speak. And so the API, as I kind of alluded to, is very similar to existing free-based approaches. It's a little bit simpler because some operations are kind of combined. The major disadvantage of it is that it is not something that you can just sort of plug into an existing monad transformer stack. It fundamentally assumes that the sort of base monad is either IO or identity, right? So either you have a pure computation or you become computation running in IO. So if you have some code that is running in some other monad that you want to interoperate with, it's a little bit more complicated to do that. And unfortunately, that's just kind of necessary in order to make the delimited continuation stuff work. But there are some limited possibilities to make some interop happen. So it's still something that I'd like to explore in more detail. But I think for the most part, aside from that, which is admittedly a significant detail, the API is pretty pleasant and pretty similar to stuff that already exists.
Oh, that's cool. Final question. Are you still working on Hackett?
That's a question that's quite unrelated to this talk, and the answer is no, not really. It's something I'm still interested in, but it got to a point where I just realized that some of the problems would just be a lot of engineering efforts, and as something I was doing in my spare time, I just couldn't really justify it. Maybe I'll get back to it at some point.
Okay, thank you so much for the talk. There's really good feedback in the talk discussion channel. I think everyone was very excited to see it, and you definitely delivered on everyone's expectations. So we're going to be back with a few closing words for ZuriHac in 10 seconds. Thank you again, Alexis.
Thank you so much.
Hey, everybody. So this concludes ZuriHac 2020. I want to thank you all for coming. I see we still have 300 people tuned in. We had about 1,200 people registered. And so that's about a similar scale to what we had physically in person. So I'm really happy about that. And all of the main organizers, we knew that it was going to be a quite interesting experiment. No one has ever held a live event before, none of us. And we're really happy how it turned out. So I want to specifically thank all the people who gave talks, everybody who gave the GHC track, the advanced track, the beginners track. We're really grateful to you, because without you, this couldn't have been this nice. And also, I want to thank you for being a really cool community. So we were not sure how much work we would have to do in Discord to manage and moderate everything, but it was just no work. It was really, everybody was extremely pleasant to each other. And we really appreciate that. That makes organizing an event like this extremely, much easier to do. We will leave the Discord open for a while. So feel free to continue hacking on projects. We will not kick you out. Don't rely on it being around still in a year, because maybe we will archive some of the project's channels. So if you really care about chat history, then come talk to me, and there are some tools that let you download the chat history of a project. Otherwise, feel free to just keep using it. And yeah, Bika, you want to say a couple of words maybe?
Yes, so again, thank you for attending this year. The shop is still going to be open for a couple of weeks. If somebody still wants to buy one of our t-shirts, stickers, hoodies, or sweatshirts, I have one of the t-shirts, looks like this, the peach one, or one of our stickers. All the profit we're making in this shop will go to a COVID-19 related charity. So buying a t-shirt is good.
So in case you liked ZuriHac, there are two other conferences I wanted to mention as well. The first of those is MuniHac. So for a couple of years, ZuriHac has had a sister conference in Munich called MuniHac. MuniHac is also going to be organized online in the weekend of 11 to 13 of September. And the organizers are going to announce that soon. You can find more information about that on munihac.de. We will also post the links in our Discord. The second conference I wanted to talk about is Haskell Love. This is a new, exciting online conference with Simon Peyton-Jones as keynote speaker, and that's also happening online from July 31st until August the 1st. And you can find more information about that on the website haskell.love. I give it to you, Farhad.
Yeah, we would also like to thank everyone again who helped us organize ZuriHac 2020. And we hope that we will be able to welcome you to ZuriHac 2021 in person at the HSR. I guess that wraps it up. Have a nice evening, everyone.